What's up, guys? It's Mr. Brengle, and today we're going to be talking about resistance and how that is affected by the length of the wire or the area, a cross-sectional area of a wire. So let's jump right into it here with the resistance and length trophy. So it says 3 gold wires are shown. Each have the same cross-sectional area, but a different length. Rank the resistance values of the wires in order from smallest resistance to largest resistance. So basically, your process for this is going to be the same no matter what. I want you to, let's use an analogy here to talk about this. Let's imagine you're out in the hallway during a passing period, and you have to walk from one classroom to the classroom that's just the next one down the hall. Okay, right next door. Not too hard, right? You're probably not going to run into too many people. It's going to be pretty easy to move there. Versus if you have to walk from the very end of one hallway all the way to the end of the other to get to your classroom, you're going to bump into more people. There's going to be more people in your way. It's going to take you longer to kind of navigate through that. And that's the idea with the length of a wire. So the electrons, as they're moving around, they're bumping into each other. They're bumping into the walls. So the more opportunities for the collisions, the more resistance. And so the point here is that a longer wire, just like a longer hallway, it's going to be harder for the electrons to move through. So a longer wire has more resistance than a short wire. Okay, so the smallest resistance is always going to be associated with the smallest or the shortest wire. So B is the shortest, A is the middle, and the longest wire that will have the greatest resistance would be wire C there. Okay, and that's all you're doing for this particular level. We're just ranking basically the length in terms of smallest. So again, the shortest wire would be the smallest resistance, and then the middle wire C would be the next one, and then the most resistance is the longest wire, which is B here. Okay, so I'm going to go ahead and head back to the main menu. That's good enough. And we'll talk about cross-sectional area now. So you can see that in this situation, all the wires are the same length, but now they have different cross-sectional areas, meaning like thin wire or thick wire. And so for this analogy, we'll keep it out in the hallway during a passing period. Imagine if they cut your hallway in half. And in terms of the width of the hallway. So the hallway is normally like this, and they cut it in half, and now it's a much thinner hallway. Again, going to be a lot harder to move through the hallway. You're going to be running into more people because now you're all in a condensed space. So the population density, so to speak, in the hallway will be much higher because now there's less area to move around in. So the thinner the wire or the smaller the cross-sectional area, the more resistance there's going to be. And the wider or thicker the wire is, the less resistance there will be. So our smallest resistance is going to be the thickest wire, which in this case is A, and then the middle one would be C, and then B is the thinnest wire and will have the most resistance here. Okay. So we'll do a couple of these. So again, the thickest wire here, A, is going to be the smallest resistance, the most room for those electrons to move around, and then C, and then B, because B is the thinnest, and there's going to be a lot more collisions there. Okay. So again, we'll head back to the main menu. I think you're good enough. That's good enough on that. You can get that last one on your own. And then the last one, putting it all together, it's going to include length and cross-sectional area. So what we're going to be looking for here is the one that has the least amount of resistance would be the shortest with the thickest wire, like shortest, thickest wire is going to be the least amount of resistance, right? Because short wire has smaller resistance than a long wire, and a thick wire has less resistance than a thin wire. So in this one, A is clearly not only the shortest, but also the thickest. Then C is the next shortest and the next thickest. And then B. So that's how we'd rank these, because B is a double whammy here. Not only is the wire very long, but it's also very thin or has a small cross-sectional area. And so this one is going to have a lot of resistance here. So And we'll just do a couple examples. So again, we're looking for short and large cross-sectional area or thick wire. So short and thick wire would be B. That's going to be our smallest resistance. Then the next shortest and larger cross-sectional area would be C. And then the long, thin wire is A. That's going to be the most resistance. Okay. So we'll do this last one. I'll let you do the rest on your own. Again, we're looking for short and thick for small resistance. And then middle would be C. And then the most resistance would be B. Okay. And this isn't part of the concept builder, but I always think it's another thing that affects resistance is the heat of the wire. So if you heat up the wire and it gets hotter, it'll have more resistance. And the reason for that is because when you heat up those electrons, they're going to move a lot faster. They're going to be bouncing around more. They're going to be running into each other, more collisions. And I always like to say, what would happen in the hallway if during the passing period, everyone was sprinting? So everybody just starts sprinting out in the hallway. It'd be absolute chaos. You'd have people running into each other, bouncing off walls, falling over, tripping over people. It'd be crazy. Would be kind of a fun social experiment, but not practical because someone will get hurt. Anyway, that's going to be your resistance ranking tasks concept builder. And make sure to let me know if you have any questions.